Our next speaker will be Professor Andreas Weiermann from the University of Ghent, who is excellent in the use of ordinal numbers and of the painting brush, as you can see. So, please.
Yeah, thank you very much. I hope that you can see my screen and that you can hear my voice. I'm giving a sort of unconventional presentation because I use my iPad with an Apple Pen. And to start with, well, in the afternoon I did a drawing of Vladimir, but for doing a better drawing I need a better photo. So I just go to the next one. So this is maybe better suited for a birthday conference. So this is one of my better paintings. It's a naturalistic painting of a rose. But of course, this has nothing to do with my talk. My talk is about accessible independence results in terms, oops, what's this? Results in terms of addition and multiplication. And in part, this is joint work with Harvey Friedman. And what is the goal? The goal is to have results which can be explained to students from secondary school, but which are independent of certain theories. And the theories I have in mind, piano arithmetic and extensions. So what is the goal? The goal is I start with terms. And I start with easy terms. So I'm saying I want to cover material for secondary school. So the set of terms is called T. And then the rules are, one is a term, first rule. B, if I have two terms, T and U, then T plus U is a term. And C, if T and U are in T, then T times U is in T. And I assume I want to have different terms, so I assume that T is different from 1 and 1 is different from U. This is a set of terms. So this looks plausible, and one can explain this to secondary school students. Now, if I have a term T, I can associate to a term T a value, T of n, which is a natural number. Now, even this can be explained to secondary school students. And what's the idea? Well, for example, the value of 1 plus 1 is 2. And the value of 1 plus 1 times 1 plus 1 is 4. Now, this can be done by secondary school students. And of course, 1 plus 1 is less than or equal to 1 plus 1 times 1 plus 1. Because 2 is less than or equal to 4. But there's a reason for this. There's a more intrinsic reason why 1 plus 1 is less than or equal to 1 plus 1 times 1 plus 1. Namely, it turns out that this term here is a subterm of the right-hand side. Maybe I take that term. And so there's an immediate reason why the left-hand term is less than or equal to the right-hand term. This gives rise to a specific definition. The definition which I want to discuss is the following. I say S is immediately less than or equal to T if S less than or equal to T holds for obvious reasons. Now, what are obvious reasons? Well, if I take a term in T, so I say less than or equal to is the least binary relation on T such that, first of all, 1 is less than or equal to T for every term T. The reason for this is I omitted the number 0. So that's quite clear. And if the term S is immediately less than or equal to term T, then of course S is immediately less than or equal to T plus U. Another implication I have, if S is immediately less than or equal to 2, immediately less than or equal to T, then S is also less than or equal to U plus T. And one has next rule. If S is immediately less than or equal to S prime, and T is immediately less than or equal to T prime, then S plus T is immediately less than or equal to S prime plus T prime. And one can make easy arguments for this, which can be understood by elementary school kids. Namely, if you have one pigeon and you distribute it over an arbitrary number of holes, then it's easy to see that there's enough space. If you have S pigeons and you can put them into enough holes, then of course it's clear that if you have the same number of pigeons and you add some more holes on the right-hand side, then of course you can put pigeons again into the space. And the same holds if you have these pigeons. And yeah, you are allowed to do the pigeons into 4 holes. If you add space to the left, then of course you can put the pigeons also into the new collection of holes. And if you have the situation of, let's say, some pigeons fitting into a larger space, some more pigeons fitting also in larger space, then of course it's clear that if you take the union of those pigeons, then you can put them into this type of space. So these inequalities, this notion can be explained easily to secondary school students. Now this covers the additive terms, but of course we have the same laws for the multiplicative terms. So we have E. If S is less than or equal to T, then S is less than or equal to T times U. And if S is less than or equal to T, for obvious reason, then S is obviously less than U times T. And G, if S is less than or equal to S prime and T is less than or equal to T prime, then we have that S times T is less than or equal to S prime times T prime. Okay, this is a canonical notion, and I would claim this relation is natural. Now, one can sell this to secondary school students, as I hope. Now, consider the following assertion. So I have to check. Got something? No. So let a certain principle, the finiteization of additional multiplication, be the following principle. For numbers k, there exists a number, well, let's first fix a binary relation. Let's say such a relation on the set of terms T. And then FAM with respect to this binary relation is the following assertion. Namely, for all numbers k, we find the number m such that for all sequences of terms a0 to am, if certain property holds, if we have that for all I is less than or equal to m, we have that the value of AI, the numerical value, is bounded by, say, k plus I. So what does this mean? This means the terms are bounded linearly in value by k plus I. Then there exist numbers I less than j, such that AI is in relation with AJ. That's somehow a complicated statement, but as it stands, it will be a pi02 statement. Because these quantifiers here with this side condition can be considered as a bounded quantifier. Now, what can be said about this principle? Well, consider the following relation. Let S less than or equal to T on terms be defined by saying that the value of S is less than or equal to the value of T. Then we can ask, well, what is with this relation and the principle FAM? Then FAM is true for this relation on terms. Now we can check that this is an obvious property. Why is this the case? Well, let us consider the assertion. So we start with k. Let k be given. Now to figure out what is m. In this case, it's completely simple. We put m equal to k. So it's not spectacular. And now assume that we have given a sequence. Let A0 to AM be given with the property that the value of AI is bounded by k plus I. Then, of course, we know something about the first value. Namely, what do we know? We know that A0 is value bounded by k. Now, what can happen? Well, it could be that one of the later numbers is bigger than k, or at least as big as k. Then A0 would be less than or equal to one of the later numbers. So if the values of AI of n are, let's say, if 1, AJn is bigger than k for some j, bigger than 0, then we are done. And the other option is that otherwise, all numbers AJ are less than or equal to k. But look, what is the situation? We have the pigeonhole principle. We have to distribute, well, this sequence here has length k plus 1. Now we have k plus 1 many pigeons. And we have to distribute the pigeons over k places. And remember, we start the terms having at least number 1. So we have here k holes. So this means, for obvious reasons, if you have to distribute these numbers over k places, 2 have to be equal, and then the values are the same. So we are done. So this principle FAM for the less than or equal to relation is a natural principle. And it's true for obvious reasons when one has the standard less than or equal to relation. Now, let us consider the following situation, namely, consider the situation for FAM, but now I replace the less than equal to relation by the relation being obviously less than equal to 2, being obviously less than or equal. First of all, my argument is this is natural. Why is this natural? Because this FAM principle just speaks about numbers. And I tried to argue that this relation here is also natural. Okay, the next theorem is then FAM with this relation is true. But this is a moment where secondary school students will not be able to prove this, because this needs the proof is difficult. And the reason is assertion B, namely PA, does not prove this. So with the standard secondary school argument, you're not able to show this. So this is in some sense a very natural independence result for arithmetic, but one can prove more. In fact, even predicative analysis is not able to prove this. So we have a strong principle, and it comes from very simple concepts. Now, what is behind all this? The hint is, of course, previous material proved by Harvey Friedman. But I transformed this result into a result just on natural numbers, and I eliminated all concepts which might not be accessible to secondary school students. Okay, that's my first thing which I wanted to show. Now the next thing.
Can I ask a short question?
Yes.
About B, as you wrote it, the sentence FAM of this relation is not even a first order sentence as you wrote it. So how can it be provable in PA in the first place? Without coding other things that you certainly cannot expect secondary students to understand. Not to say they're not going to understand the claim itself, but that's another matter.
Well, let us look. What is the statement? The statement is just this one, right? So for all k, there's an m such that for all sequences of terms, if this property holds, then this property holds. For this, it's not even necessary to understand what PA is. You just speak about, given k, there's a number m so big that for all elements of my terms, and those terms are things people have seen in secondary school. Then I say, look, when the values are linearly bounded, then I find some numbers I and j, less than equal to m, such that the first one is less than equal to with respect to index t, the second one. So for this, I don't need any formalization, no codification. It's just a statement which I can explain to secondary school students. For this, they have not even to know what Peano arithmetic is. But the proof methods students see at secondary school will be contained in Peano arithmetic. So they will not see difficult arguments, even I guess that they don't see complete induction at school. So they will have big problems in proving something. Now, if you go to this assertion here, it just says that it's difficult to prove it. I'm not claiming that part B is understandable by secondary school students. I'm just saying that secondary school students can understand this assertion. The unprovability assertion is different. It just says for the logicians that there's internal strength involved and that even predicative analysis is not strong enough to prove this. The next question I want to discuss is, well, I have studied terms. Now the next thing is what happens when we identify terms modulo commutativity. So what about identifying terms, namely s times t is the same value as t times s, and s plus t is the same value as t plus s.
Can I?
Yeah.
Can I interrupt? Can I ask? But this is for the rule-based less than or equals, not for the regular less than or equals. So maybe Arnon is interested in how you define that, because don't you have to talk about, you write some rules down, but then you have to talk about these rules being, how should I put it? Two things are less than or equal to each other, just in case you can obtain that from the rule, from iterating the rules.
Yeah,
right?
That's true.
So maybe the issue of whether that's first order is what Arnon is worried about.
Maybe, but let's say for school kids, it's enough if I give enough examples and then at some moment they believe that they understand the relation, even if they don't understand it in full.
All right, but formally you're taking this to be the rule, the relation generated by rules, right? That's
yes.
Between professionals, that's what you're talking about, right?
Yeah. Anyway, but let me now continue. So I transfer this relation into a new relation with a prime, and it's just extending the old roots. This is essentially the definition of this one, plus what do I need? I need the following roots. If S is less than equal to prime T prime, and T is less than equal to prime S prime, then S plus T embeds into S prime plus T prime. And the same holds for multiplication. So there's a certain asymmetry that this term here goes to the right-hand side and this term goes to the left-hand side. And here is a prime missing. So if one adds those roots, then of course one identifies more terms. And the question is what's going to happen with the principle. The theorem is FAM with this new relation is still true. Of course, this follows from this assertion. Oops, from this assertion over here. But more surprising, or somewhat surprisingly, PA still does not prove this statement. And in fact, RTA0 also does not prove it. The next thing which I want to discuss is a natural property, namely associativity, namely S plus 2 plus U can be identified with S plus T plus U. And S times T times U is the same as S times T times U. Now one can define the ordering relation in a way that such terms are, let's say, equivalent modulo the ordering relation. This leads to a canonical extension of the relation. So this relation is extended to a new relation, modeling associativity. Now what's going to happen is the next theorem is A, that FAM is still true for this new relation, and B, the arithmetic does not prove FAM with this new relation. And as you might expect, RT0 also does not prove it.
Here you mean associativity alone or together with commutativity?
That's a good question. Actually, in this statement, I mean it alone. But then the next question is, join them together with commutativity, and it still remains the same. So if I plug in the new relation, it's commutativity plus associativity, then the same. The same means I still have this one here, of course. It's independent of RTA0. The next question is, what about distributivity? But distributivity means that multiplication somehow loses its power. So this makes this statement weaker and becomes provable in that theory.
Mm-hmm.
Aha, that might be somewhat interesting. Now, phase transitions can be done for this situation. So what is phase transition? I write down a principle, FAM, with respect to function f. It's a statement in the relation less than or equal to. The following principle: for every k, there is an m such that for all sequences of terms, if for all I less than or equal to m, we have that the value of an is bounded by k plus f of I, then there exists I less than j such that a of I is in relation with a of j, and this is bounded by m. Let fr of I be r times binary log of I, maybe rounded to the next integer, it doesn't matter that much. And then you can ask for which numbers r is the principle true. It will be true for every r. For which r is it provable in PA, for which r is it unprovable in PA. For this I have to copy a number. Let's see where it is. Here it is. So I write down a number. Let C be the following number. It's 4 times 0.765617852760 and it's presumably an irrational number, maybe transcendental. It's a little bit bigger than 4. Rho, let rho be 1 divided by binary log, true binary log of C. And then one has A. If R is less than or equal to rho, then PRA does prove FAM with respect to FR and this relation. And B, if R is bigger than rho, then PA does not prove this assertion. So this number rho over here is the threshold for provability in this context. Now this threshold changes when you go from this relation here to the other relations. Actually, this is not yet determined. I don't know yet, but this is a future project. Other options are modifying here this context here by functions like integer complexity. And I'm in contact with experts in this integer complexity business, and I want to investigate what type of thresholds will be obtained when one has other conditions over here. But as we have heard, Harvey Friedman has challenged me to try to replace this relation here. Namely, since it's inductively defined, it might be better to replace it directly by the less than or equal to relation. And the question is whether I can do so. And I have two answers for this. And maybe I come with the newest example. So there are two examples which I have. So example one. And for this, I just want to have a result only in natural numbers. And for this, I need base k representations. So I say, well, first of all, we have to know for all numbers, let k be at least as big as 2. For all numbers m, there exists unique numbers r, p, and q, such that m has a form k to the r times p plus q. Let's assume that m is bigger than 0. What else do we have? There we have that k to the r is less than or equal to m, strictly smaller than k to the r plus 1. P is smaller than k, and q is smaller than k to the r. By the Euclidean algorithm, division with remainder, one can show that there are unique r, p, and q with this property. And in this sense, I can say that m has this form, this so-called k-normal form. With a k-normal form, I define base change operation. Namely, I replace base k by number L. And this means, well, go into the base k representation and define it inductively by replacing this k by L and do it hereditarily in R and Q. It will be L to the R, where I do the replacement, times P. Well, note, P is smaller than K, there's nothing to replace. And I do the replacement in Q. If M is in K normal form equal to K to the R times P plus Q. Now, when I fix this notation, I can write down the following statement. G is the following statement. For all K, there's an M such that for all numbers A0 to AM, now I switch from terms to numbers. If I have for all I less than equal to M, if I take AI, I replace in AI base I plus 2 by number 2. And if this number is less than equal to 2 times k of I. So I have not yet defined this, but this is the usual notion. So 2k of L is just a tower of 2's of height k. And on top, I put an L. So I have an iterated exponential of height k. And on top, there's a number, in this case, a number I. If this holds, then there exists an I less than M, such that if I take AI, replace base I plus 2 by 2km, then this is less than or equal to, I take AI plus 1 and replace base I plus 3 by 2km. Now, this is again an arithmetical statement. Only speaking about numbers. What I need here is only the notion of replacement of a base. And then you can ask how strong is this principle? And this principle is the following strengths. First of all, it's true, G is true. And second one, PA does not prove G. So this is somewhat similar to the first example, but I switched from terms to numbers. In this sense, it's more immediate. On the other hand, I have to use here the base K representation, but this is still somehow in the scope of secondary school, because division with remainder is something at least what you can do in concrete situations when you have concretely given numbers. You do it, and somehow you can explain this. So this is hopefully not too bad. This is example 1. And example 2 is the following one. I have exponential terms. I'm paying a price. I'm coming back to terms. So what are exponential terms? Well, it's terms in one variable. So 0 is a term. And if A and B are terms, then I form the term in variable x. I take x to the a plus b. And this is a term. Now, if I have a term, I don't know the value. But if I have a number k and n, I can form a k. What does this mean? Well, I take a, set variable x to k. So I plug in the numeral for x, the case numeral for x, and then I take the natural number for it. So this is also some sort of substitution. And using those exponential terms, I can write down the following statement, namely exp. I call it differently. How do I call it? Call it slowly well-orderedness of epsilon 0. Well, I should not call it of epsilon 0. Slowly well-orderedness of exp of slowly well-orderedness, just because it's the following principle. For all k, there's number m, such that for all terms a0 to am, if for all I less than equal to m, we have that's well, I take ai, and now I replace variable x by 2. This is less than equal to 2ki. Then there exists an I less than j. There exists an I less than m, such that ai, where I replace variable x by 2km, this is less than equal to ai plus 1, where I replace x by 2km, and I do the evaluation. Again, this principle, theorem, this principle SWO is true, and B, PA does not prove this principle. And there's no end with these principles, namely one can strengthen all of this. The canonical idea here is we have here terms in plus and exponentiation, but you can ask, well, what is going on when you involve the Ackermann function? It's possible. And then one gets here an independence result for RTA naught. You can plug in here functions for the fast growing hierarchy, formal terms for these things, for the so-called F alpha, where alpha is less than epsilon 0. Then one gets here an independence result for stronger theory, namely ID1. Something similar can be done for the previous example. And this is a rather open-ended story. And Harvey Friedman has similar results, so not similar results, but results of the same nature, namely results just speaking about numbers less than equal to, which are also quite strong. So, the plan is to throw all these things together to make some nice paper out of this. Okay, this is basically what I want to say. And to end after this long discussion, I want to show some trees, which I painted. This is a watercolor, and this is soft pastel. And,
Are these trees well founded?
yes, they are very fun because this is the last page. So
Yeah.
I want to
Very well founded. Grounded, I would say, yes.
Right.
anyway, so now I can stop my presentation and I'm open for a discussion.
Okay. Questions? Comments?
So Andreas, I have a question. So maybe a remark towards an answer to Arnon's question. I think I understood the question as whether as to how to formalize this statement in piano arithmetic, and the answer is yes, you can do that, but you need Gödel numbering. You need to Gödel numbering to define sequences of these terms. But
yeah,
as Andreas justly mentioned, this is not needed to understand the meaning of the the statement, which is happens to be untrue. But okay, that's one remark. But my question to Andreas was, apparently there are some well quasi orderings involved in these results on the level that you did mention. What are the maximal order types of these well quasi orderings associated with successive principles that you have? Are they of the order of Kruskal theorem, or
you can design for all these ordinates showing up in the Kruskal business corresponding terms which match these order types. So with plus n times, one only gets order type gamma 0. But for example, you can introduce symbols for variadic addition function, and then you get full Kruskal's theorem. So it depends a bit on how you are organizing your term system. If you allow a variadic function symbol, then you immediately get a full Kruskal's theorem. So there are all sorts of fine points, but of course I have to say the very basic point for all of this is miniaturization by Hubble-Friedman. So without the original miniaturization, these results would not have been found.
of course?
Okay, may I?
Yes, please.
Well, I have no question about the mathematical results, which are nice, and every result shows something independent of PA or other theories which one doesn't use directly, at least, any self-reference or consistency is nice for itself. What I'm not sure about is the, how it's called, the GII, the general intellectual interest of this thing, at least the way it was presented. You talk, for example, that it's connected only with numbers and plus and addition and multiplication. But then you use not only exponentiation, but double exponentiation, the 2 to the k, or with this notation. If this has to do only with the multiplication and addition, you can say it has to do only with addition, because multiplication also is only a repetition of addition and nothing else. So it's, in fact, you can say it's only results about addition if you want. And then we can say only result about successor, because addition, after all, is only iterating the successor operation. So I'm not sure that they're describing it as a simple result, or not simple, but results only about addition multiplication is the correct way to describe it. And then come also, of course, the notion of natural, which, you know, this is never be an exact notion, and what is natural for people like you especially after you work a lot with these kind of things, then it became very natural for you. While not, for many years, question of consistency were the most natural question of the world. You know, the Hilbert famous list, consistency was one of the main problems. So who can say it's not natural, but we take it as not natural now, unnatural now.
Yeah. But look, so in the very beginning, I had a set of terms T, right? So we have three roots. One is a term, and I close under plus and times. So these are clearly statements about terms involving addition and multiplication. Now the evaluation of those terms is also easy. Addition function is interpreted as addition. Multiplication function is interpreted as multiplication of numbers. Now I write down this relation over here, and this relation only involves properties of plus and times. And these are very natural properties.
Yes, but the least binary relation such that is not so simple.
Yeah, well, but just look at this statement.
This you need transitive closure and think of this sort and in fact iteration even. But if you do, but that's what you.
Yeah, but anyway, I have the relation. I say one term is obviously less than or equal to another term, and I'm claiming that I can sell this relation to students from secondary school. And then I write down this principle FAM. And when you look at the definition, what is involved? It's number K, M, sequences of plus and times terms. And then I do the evaluation. I have a growth rate condition, a linear growth rate condition. And for the rest, I'm just saying that one term fits into a later term. So just this statement as it stands is not too bad, I would say. Well, only when I eliminated the terms in favor of numbers, I jumped to the iterated exponentials. But in the very beginning, I was just staying in terms of plus and times. Of course, there's something to be said about this. To formalize the definition is something else. But still, I believe that one can explain this to students, to secondary school students.
Once one gets to these debates and issues about conceptual simplicity, I think it's best to, one good thing to do is to jump to the future and ask what the shape is of what would be ultimately totally best, or a maximum point. And I have some ideas about what that would be, but that's a different kind of, I'm not talking about exactly what we know how to do right now. I'm talking about what would be logical path feasibility. I don't mean just making nonsense like the Riemann hypothesis is independent of a measurable cardinal or something like that. I mean something more plausible. Do you have any? I have some ideas about what might the ultimate things look like, but what do you have you thoughts along these directions? In other words, what do you want this to look like 10 years from now?
I have no idea. So I can just say that these results are basically 3 or 4 weeks old, so, and now difficult to make predictions for the future. But the point is, they all emerged from more or less from interaction with Harvey Friedman, and this is something which I like very much. It's a bit of playing ping pong. One does this, and then I get this answer, and then one does something new. And the only thing what I'm thinking about now is in refinement is doing phase transitions for the later examples. So it could be that it might be that I can get rid of these iterated exponentials, but at this moment I'm a bit careful in making claims because, well, first one has to prove results, and then one can look at fine polishing, but one should not start just with some bold claims and then one is stuck.
All right, you might enjoy, here's a thought, okay, for the future.
Mm-hmm.
You write down a simple function from natural numbers to natural numbers. It may be, you know, something that it may be something that has exponential or gamma function in it, or round off because you're doing division or something, but I mean something really tiny. And you argue that if you iterate this, then it goes to zero. And that statement, if you iterate this, it's got one variable in it, X. Okay, so no matter what you put in for X, this thing always goes to zero, and then that's independent of ATR naught, say.
Yeah.
In other words, you're just talking about, and you display the function. It's tiny by any measure of anything, because it just has, say, three or four operations that all mathematicians use every day, like plus and times, or division, or round off, or maybe something factorial or something, or I don't know what, logs and so forth. But it's actually absolutely tiny. There's something like 8 symbols in there or something. And then you ask, and it does have a variable X in it. And you do ask whether for every X does this go to zero if you iterate it. And that's a pi02 sentence, and it's all over the place in the logical hierarchies. So I mean, that's for example. So that's pretty uncluttered, because you just talk about writing down one operation. Now we know that this doesn't work very well for -1. I mean, assuming you want it to, you do get zero pretty easily. Even anybody can. The elementary school kids can actually prove that, right? That if you take prove in quotes that if you take a natural number, you get to zero if you subtract 1, iterate it. So it's got to be more complicated than -1. So how much more complicated does it have to be? And in fact, can you show, for example, that if the functions only have a few symbols in one of the standard collection of functions that mathematicians use, that there's no such result like this, that you always get termination or non-termination with small combinations. But then at some point it becomes mysterious, and then somebody from the future comes in and says, well, if you use 9 symbols, just 9 symbols here, it corresponds to the consistency of ZF. Now, what do you think of that? I mean, not that I have any idea how to do that, but I'm just sort of mentioning some goal, that's all.
Yeah, well, so what I would say is just a pragmatic approach. Just it would be interesting to look into this, and then after some time you can either come up with something or you are stuck.
But it does have the way I formulated it. It does have a workable project, namely to show that you can't do it with 2 or 3 symbols like that, or 4 or 5 or whatever. It does immediately suggest a weak partial results, and so I think it's good. I think it's a good idea to just sort of up the ante 25 levels into something that you have no idea how to do, and then see what you can say about it being impossible, or at least having some prototype of the future.
Yeah, well, interesting project, but of course at the moment I cannot say too much about this. So what I really would like to see is getting rid of these iterated exponentials. And the question is, what type of phase transition is available for these latest results? And well, what? Yeah. So the idea would be to have just a result in numbers, only involving plus and times, no iterated exponentials. But maybe I don't know whether this is possible. So what type of tricks one could use. But well, the most canonical example one knows is the Goodstein result. But the Goodstein result is not flexible in the sense that it depends very specifically on writing down a specific sequence, and there's not much choice to modify it. And
you looked at a lot of modifications of it. Is it brittle? If you modify it a little bit, it collapses into provability or refutability?
But what is needed is the notion of a K-normal form. And what I believe is a notion of a K-normal form is key for what I consider as a theory of denotation systems for natural numbers. So there's a theory of ordinal notation systems, and there will be a theory of notation systems for natural numbers. And the notion of K-normal form will be crucial there. But the question is what type of normal forms you have available, what makes sense in this context. And up to now, I'm working with plus exponentials and iterated Ackermann function type things. But there will be more things about this. So the next one is to include multiplication, maybe factorial. But this is all just at the beginning, so we don't know. So we just have to see.
There is one comment about the mode of presentation of this material. When I did the miniaturization of so-called finite form of Kruskal's theorem, there was in the background Kruskal's theorem very clearly stated. In other words, the infinitary forms were very clearly known and stated. And I'm saying that I'm doing a certain kind of finitization, right, back in 1981. But with your presentations, I think it might be helpful to have a part that's not for high school, elementary school. See, I do gifted high school, which is much easier, right? But rather than talk about elementary school kids right off, behind this are infinitistic statements, right?
Yes.
With high proof theoretic ordinals, or from not so high to high proof theoretic ordinals, and that's already of course an important, interesting subject. And you're talking about a whole bunch of new ones like that where distributivity, commutativity are related to the way that the trees are presented, right? Whether they're, what do you call it? Whether they're structured trees or not, and so forth. So there's this background stuff that's not for elementary school, that's behind a lot of this, or all of this actually, right? And now I know we in our joint paper this is going to certainly be clearly present, because one of the authors is going to insist on it. But but I think that in the talks, maybe it might be a good idea to put some of the infinitary stuff that's behind this up front and specifically. What do you think?
Well, it's a question of what one likes most, but it's a bit mysterious just writing down the statements without giving any hint, to say.
No, but I'm talking about the hint is that there are these infinitary statements behind them.
Yeah, but then they are maybe not so surprising any longer. But now I'm just starting.
In other words, you're designing this talk to be surprising more than informative.
Yeah. Harvey, that it does really matter, because there is always some left in the room which will ask this question. If you miss this, the technology behind it, somebody will ask the question, and you'll be forced to answer it anyway.
Yes, but I explained that I used harvest miniaturization, so that was the machinery I used. And
Yes, I enjoy it very much when I hear about that. Yes.
No, I think it is also a good point that the last remark by Harvey, that one should not hide these things, because they're also beautiful. So why should we artificially hide them?
Well, depending on the audience, of course. For us, it was probably wiser to reveal it up front.
Yeah.
Yes, I'm talking about us here. I'm not talking about the elementary school expeditions.
Yeah, if it was a lecture for children, which could be actually on this topic, certainly it would be nice to hide them first and then somehow see what happens. But yeah, anyway.
Try both, and Harvey also try both and see how it goes.
Yeah. Anyway, I guess we have to give the word back to the chairman because it's already.
Yes. So
I have a question about your strange constants, about this connected with this phase transition. How many do you know? Really different constants.
Well, I know the constant for these specific terms, but not for modulo commutativity and associativity. And I'm working on this. But this number is already special. And well, when you look on it, when you look for it, you will find it with a Google search. But you have to know.
It would be wonderful if it turns out that the constants in the phase transition, whether they're rational or not, is also independent.
Yeah.
That's a good question, but I have no idea. But they are primitive recursive. So, but irrational questions is a different question. Yeah.
okay. So I think we finish the discussion now and make a break, say for 5 minutes, and we will start punctually at 8 o'clock and 5 minutes with our next lecture. Thanks.